Have you ever stood near a huge dam and just felt that power? The sheer force of all that water being held back. It's pretty amazing to think that the simple act of that water falling can light up an entire city. It's not magic, but it is one heck of a feat of engineering. So let's get into it. How we turn water into watts. So yeah, that's the big question, right? How exactly do you go from a massive, calm lake to the electricity that's powering your screen right now? It's all about a journey. An energy transformation that starts with just a little push.
At its core, it all boils down to this really elegant four-step energy swap. First, you've got all that water sitting behind the dam. That's stored or potential energy. Ton of it. Then you release the water. Whoosh! All that potential energy turns into kinetic energy, the energy of motion. That powerful flow then spins a turbine, giving us mechanical energy. And finally, that spinning motion gets turned into the electrical energy that powers our world. Simple as that.
All right, so let's zoom in on the heart of the whole operation, the turbine. This is ground zero, the exact spot where the raw, wild power of moving water first gets captured and turned into useful rotation.
Now you can't just slap any old turbine in there. It's definitely not a one-size-fits-all kind of deal. Engineers have to pick the perfect tool for the job. If you have a really tall dam, but maybe not a huge amount of water flow, you'd use a Pelton wheel. Think of it like a water jet blasting into a series of little buckets. For something in the middle, like the Hoover Dam, medium height, medium flow, the Francis turbine is the go-to workhorse. And if you've got a lower dam but a massive volume of water, you bring in the Kaplan turbine, which looks just like a gigantic propeller from a ship.
And get this, these turbine blades are so much more than just simple paddles. They're seriously high-tech. They're actually shaped just like an airplane wing, using the same principles of fluid dynamics. As water flows over that curved shape, it creates a difference in pressure, and that pressure difference generates lift, which pushes the blade and spins the whole turbine with incredible force. It's literally the same science that keeps a jumbo jet in the sky, just flipped around to make power from water.
Okay, so the turbine is spinning like crazy. Great. But how does that spinning bid us a spark of electricity? Well, that's where our next piece of equipment comes in, the generator. Let's see how this thing works its magic.
The secret sauce behind the generator is a principle called electromagnetic induction. It was discovered by the absolute genius Michael Faraday. Now, I know it sounds super complicated, but the basic idea is shockingly simple, and it's the foundation for pretty much all the electricity we generate on the entire planet.
Here it is, the core concept. If you move a magnet near a coil of wire, you get the electrons in that wire to start moving, and that's an electric current. That's it. That's the whole game. A moving magnetic field creates electricity. Everything else is just figuring out how to make that process bigger and way, way more powerful.
So here's how that plays out inside a generator. The turbine is connected to and spins a rotor, which is basically a giant, powerful electromagnet. That spinning rotor is sitting inside a stationary ring of tightly wound copper coils, which is called the stator. So as the rotor spins, its magnetic field is constantly sweeping through all those copper coils, and that moving field shoves the electrons along, creating a huge electric current. It's such a beautiful relationship. Spinning magnet, still wires, and bam, a flow of electricity.
All right, we've got our turbine and we've got our generator. Now let's pull the camera back and see how all these pieces fit together into a complete hydroelectric plant. It's a massive system, all designed to get that power from the river all the way to your house.
Every single part of this system is crucial. The reservoir is like the giant battery, storing all that potential energy. The water then goes through an intake and down a massive pipe called a penstock, which really builds up the pressure before it hits the turbine. The powerhouse? Well, that's the industrial heart of the operation, where the turbine and generator live. From there, transformers and transmission lines get the electricity ready for its long journey to the grid. And finally, the water flows out through the tail race and back to the river. It's job done.
You know, trying to send electricity over hundreds of miles is kind of like trying to send water through a really long, leaky garden hose. You lose a lot of pressure along the way. To solve this, transformers step up the voltage to insane levels. We're talking from maybe 25,000 volts up to 500,000 volts. This super high voltage lets the electricity travel for miles and miles with very little energy loss, making sure the power made at the dam actually gets to our cities.
Now this is one of the coolest parts about modern hydropower. Some of these plants can actually work in reverse. So when demand for electricity is low, say in the middle of the night, they can use cheap power from the grid to pump water from a lower reservoir back up to the top one. It basically recharges the dam. It creates a giant water battery. Then during peak hours when everyone needs power, they can release that water all over again. It's a brilliant way to store huge amounts of energy.
So, we've seen the incredible engineering that goes into this. But what's the bigger picture? Where does hydropower fit in our energy mix today? Well, it's a story of immense power, for sure, but also one with some pretty significant challenges.
The global impact of hydropower is just staggering. It provides about 16% of all electricity worldwide. But check this number out. It accounts for a massive 60% of all renewable electricity. That makes it by far the biggest player in clean energy and kind of the unsung hero of the whole movement.
But like any major energy source, you have to look at the whole balance sheet. On the plus side, it's renewable and ridiculously efficient. We're talking 85 to 90% efficiency, which is just amazing. It's also super reliable, and it's dispatchable, which means operators can fire it up in minutes to meet sudden demand. But there are big downsides. Dams can have a major impact on river ecosystems, they cost billions to build, they're vulnerable to droughts, and we can't ignore the human cost. Building a reservoir often means displacing thousands of people from their homes.
So, when you boil it all down, after all the complex physics and the colossal engineering, it all comes back to something so beautifully, fundamentally simple: water flowing downhill. It's this incredible technology that's both ancient in its basic idea and absolutely critical for our energy future. I think the big challenge for us now is to figure out how to keep harnessing this incredible power in a way that works with nature, not against it. How can we innovate to make it even better?